The sound of hysteresis. Ever wonder how these graphs sound? Suppose frequency increases from bottom to top along the vertical axis. Then the sound of a vertical line as it is traversed could be. In addition to frequency changing along the vertical axis, we also consider for the horizontal axis from left to right that loudness moves from loud to quiet. Given this, how do these hysteresis loops sound? What is hysteresis? It can be helpful to explain hysteresis via the dynamics of a thermostat in a refrigerator, which is either in a state of being off or in a state of being on. Suppose switching between off to on occurs at a temperature of 5 degrees Celsius. If the temperature is initially less than 5 and the thermostat is initially off, then as the temperature increases to 5, the thermostat switches on at 5 to initialize cooling and remains on as the temperature continues to rise. Sometime later, the temperature decreases and we wish for the thermostat to switch from on to off at a temperature of 0 and to remain off as the temperature continues to lower. The path from on to off is a different path from off to on, which creates a loop and is visually highlighted by the two differently colored paths. We say the dynamics of the thermostat exhibits hysteresis. The hysteresis loop is formed by the two different paths that are connected. Consequently, hysteresis is said to exhibit path dependence. Path dependence and looping behavior are synonymous with hysteresis. The loop occurs for temperature between 0 and 5. If there was no loop, any small temperature change at, say, 5 would cause the thermostat to frequently switch on and off, which would quickly wear down the thermostat. The shape of this hysteresis loop describes the behavior of magnetism. For example, a flexible beam composed of a magnetic material can be deformed by a magnet from one direction and by another magnet in another direction, which leads to path dependence. Consequently, this displacement in the beam exhibits hysteretic behavior.